Alright, so what we're going to look at first is finding unit vectors in the direction of another vector. So hang on, if we talk about a unit vector, recall that we said this is a vector with a length equal to 1. And sometimes usually we use a lowercase u to represent our unit vector. So if its length is 1, we could use the magnitude symbol and say that it's equal to 1. Now, we talked about how there are special unit vectors. We have the I, we have the J, and the K. All right, in 3D, here's the I, here's the J, and then the K corresponding to the Z component. All right, so remember, this is really like your X, this is really like your Y, and this is really like your Z. These were special unit vectors, and what's so special about them is they were, again, a length of 1, but the I was in the X direction, exactly 1 length, the J was in the Y direction, exactly 1 length, and the K is in the Z direction, exactly 1 length. Alright, so let's look at an example here. Suppose we wish to find a unit vector in the direction of this vector 3, negative 2. So if we were to draw this vector 3, negative 2 in standard position from the origin here, so we're really drawing its position vector. So to the right 3, down 2, so our vector here, alright, it looks like this. This is the direction we wish for it to be in. But now we need the length to be 1. Remember, a unit vector has a length of 1. This vector that we're given, the vector of 3, negative 2, has a magnitude of a lot more than 1. Well, let's figure out exactly what its magnitude is. If we do Pythagorean theorem on this, 3 squared plus that negative 2 squared, that's going to give us radical 13. All right, that is the length of that given vector. Well, we need to scale it down. We want the length to be 1. So what we do is, to find our unit vector, we take the given vector of 3, negative 2, and since anything divided by itself is 1, we know its own magnitude is radical 13. So if we were to divide each of these components by radical 13, it would actually have a length of 1. So this unit vector, if we divide each of these by radical 13, we'd have 3 over radical 13 and then negative 2 over radical 13. Now, let's run this through Pythagorean theorem to prove that this length is really 1. Okay, so let's give ourselves a little more room here. So if we're going to find the length of this, well, we know the length is going to be 1, but rather if we're going to check the length, I should say, we want to make sure that this length really ends up giving us 1. So we're just going to take these components, and if we run it through Pythagorean theorem, let's watch what happens. Well, we're going to end up with 9 over 13 plus 4 over 13, which gives us the square root of 13 over 13, which will go up here, is the same as the square root of 1, which we know is 1. So that confirms that it really is a unit vector. So the answer to the question is this vector right here. Okay, that is my unit vector that's in the direction of this other vector. And it would be helpful if we had a little mini formula. The mini formula, unfortunately, it's not given to you. If you're trying to find a unit vector in the direction of some other vector, that other vector, call it v, you would then have to divide it by its own magnitude. So this is your little mini formula, all right, and this is used to find a unit vector in the direction of vector v. Okay, so jot that down, that this is used to find a unit vector in the direction of another vector, like we saw in this example. The other vector is what we call v. Okay, one more example here on this topic. Suppose we wish to find a vector of length 5 in the direction of the vector 1, 2. So this time it's not a unit vector, but it's just another vector, but it's a length of 5. Well, keep in mind that a length of 5 is really equal to 5 times the unit vector. Remember, we're going to use a lowercase u to represent our unit vector. So if we can find a unit vector, we could then just multiply it by 5, and then we'd have what we need. Well, our formula to find a unit vector is the vector whose direction it's heading in, which we're calling v, and then divided by its own magnitude. So this vector 1, 2 is what we call v. So we need to start by finding its magnitude. So we're going to take those components, run them through Pythagorean theorem. We're going to have the square root of 5. So my unit vector, we're taking our given vector of 1, 2, and we're dividing each of those by 5, which means, and you can jump right to this part if you wanted to, we have these components of 1, 2, and each component is divided by root 5. From there, we're not going to double check it like we did in the last example, but if you were to run those components through Pythagorean theorem, you would see that the length is 1. Now remember, this is a unit vector. We are looking for 5 times the unit vector, right? That gives us a length of 5. So we're simply going to multiply each of these parts by 5. And then from there, if we clean this up, we'd have 5 over root 5, and then 10 over root 5. Now I would encourage you to run that through Pythagorean theorem to prove to yourself that you're going to get exactly 5. Okay, first thing here we're going to look at is adding and subtracting vectors. So if we are looking to add vectors, algebraically it could not be any easier. If we were looking to do vector v plus vector w, you're just going to write them out, and we are going to add these just straight across. So you're going to add like components. You'd add the two x components together. This would give us 3. Add the y components, we'd get 4. If this were in 3D, then we would also be adding on the z components. So the answer here, algebraically, is 3, 4. Now, graphically or geometrically, we sometimes call it, if we were to get a feel for what's happening here, so the vector 5, 1, if we were to graph this, this vector is in standard form, so it's coming from the origin here. So I'm going to label this vector v. So there's our 5, 1. Remember, the x is 5, the y is 1. Now, from there, we want to add on vector w. So vector w, we are going to start that at the end of vector v. So where vector v ends, we are going to travel along a path of negative 2, 3. Well, negative 2, 3 would take us, again, let's start right here at the end of v, and if we were to travel along the path of negative 2, 3, we are going in this direction, okay? So to the left 2, so our x movement is negative 2, our y movement is a positive 3, all right? So this is our vector w, and it has components negative 2, 3. Well, if we were to look at this resultant vector, this vector is represented by v plus w. And we can see that it has components of over 3 and then up 4. Okay, so we just confirmed that v plus w is 3, 4 by looking at its components on the graph. So if we are looking to do v plus w, it means we are going to add on w where v ends. Now, suppose we were to switch gears and look at vector subtraction. If we wanted to do v minus w, well, once again, algebraically, it's a piece of cake. You're just going to subtract your components straight across. So I would end up with a positive 7 for the x component and a negative 2 for the y. So geometrically, what we have to understand is that we don't really ever subtract vectors. Instead, what we're going to do is we're going to add on the negation of the vector. And so we talked about earlier in a video how to negate a vector. If we are negating a vector, what that really means is up here, I'll do negative w. We're just going to switch the signs here. We're going to just negate, in other words, our components. So negative w would really be positive 2 and then negative 3. So what we're really looking to do is we're really looking to take v, which we said is phi 1, and we're really looking to add on the negation of w, which is 2, negative 3, and of course that gives us that same result. So geometrically, what we need to look at is, okay, we have our vector v, which we said was this vector right here. At the end of it, we want to add on vector negative w. Well, negative w has components 2, negative 3. So that means we're going to the right 2 and then down 3. So from the end of v, I'm going to go to the right 2 and then down 3. That's going to put me right here. Alright, so I'm going to draw this vector, and this vector here, the one that has components of 2, negative 3, this is negative w. So that's negative w. We'll label that right in the middle somewhere. So then the resultant, the vector that connects these two, alright, if we draw this vector in, this is v plus the negative w, which of course is the same as v minus w. Okay, so think of vector subtraction as really vector addition, but you're just adding on the negation. And think of vector addition in general as just traveling down another path. So you have the shortcut path and you have the longer path. Okay. And you can see here how the answer vector, the v minus w vector, would be an x component of 7. So we've gone to the right 7 if we start here and end here, and down 2. Okay, so confirm it not only algebraically, but also geometrically. Bye-bye.